So again, we're here for ITMartini 22, in Infrastructure We Trust. And this afternoon is all about infrastructure. So if you're here for the development conference, you came to the wrong place. I'll direct you to the building down the street. The first presenter we're going to have today is the current Executive Vice President and CTO at Peak 10. He has a passion for IT, a passion for infrastructure, and a background in infrastructure. His past life and roles were in operations. He co-founded an organization called Vobix, which was currently the largest customer, was the largest customer of Peak 10, and it was the second largest Great Plains ASP. He was also in a former life a senior director at LexisNexis. And a little note about Peak 10, if you didn't know this, it's Southeast's largest data center outsourcing company. And another little note about Peak 10 is if you have a problem and can't get your pizza delivered, you need to call Jeff Biggs, because it could have something to do with him. They actually have in their data centers, they host some of the largest fast food companies and fast food organizations here in the States. So without further ado, I'd like to introduce Jeff Biggs, who's going to come up and talk to us about the trends towards efficiency in computing.
Thank you very much, Jerry. First thing I want to do is kind of paint a picture for where we are to get you in tune with why we need to have efficiency, what it's all about. So give me a minute for that. With my lovely noggin. Our agenda. We'll zip into this because we're tight on time. Why do we need efficiency? Well, if you notice a trend there, you'll see that back in 2007, data centers as a combined unit across the North American grid were chewing up about 1.5% of the energy produced. That is enormous when it's relegated to not only an industry, you could say IT, more importantly, it's relegated to data centers associated with IT. So you keep progressing forward, and you can see this year we're worried because it could approach as much as 2.5% of the North American energy grid. Again, very significant. Now, what worries us about that, what should worry everyone, is that when you become that significant, when you matter that much to the grid, what happens? Regulation happens. Got everybody worried. We started doing all this analysis. We said, PUE, that's power usage, effectiveness within the data center. We want to worry about that. We want to study it. We want to see what we can do to be more efficient. So every data center, every IT operator started to look at this and started to get more concerned, started to pay attention to it from a good perspective. A few CIOs got their first power bill from the CFO. That kind of changed a few things. We had one particular prospect come to us, and the CIO handed the power bill across the table, and he goes, if you can help fix this for me, I might be a customer. And when you start thinking about the power consumed in all of those areas, let me just say this, it's well into 7 figures a month that I pay to the utility company. They love me because we make money, we pay our bills, so I'm a constant load factor. They kind of like that about us. But to understand how important that bill is, 1 penny makes a difference. I had to explain this to a chamber because they were trying to solicit or come up with a plan where they could get data centers coming into their particular city because they have low utility rates. So just to create this example for you, if the utility rate is 5 cents a kilowatt hour, which is a fantastic rate, and across the map that you just saw there, I'm between 5 cents and 10 cents a kilowatt hour when you look at those 10 different cities. So a pretty big spread. But at 5 cents, if they increase the utility rate by 1 penny, please understand, it's $200,000 a month that you have to pay in additional expenses just to keep the lights on. So it's very significant. Power is extremely significant in IT. What happens inside the data center? Well, this is kind of a couple of charts that show you the breakdown. Consider this. Data centers, you know what they are? They're the most sophisticated toaster you can make. Probably the most expensive as well. We drink electricity, we belch heat. That's it in a nutshell, right? Nothing more exciting than that. So as you look at this, you see that the lion's share of the load in the data center is related to the IT type equipment, the servers, the disks, the networking hardware, all that paraphernalia. And then what are they doing? Drinking more electricity. Now they're creating a problem for me. They're rejecting all of that in heat. So what do we have to do with that? We have to get the heat out of the data center. So we spend an enormous amount of money on cooling. What does that take to run? It takes more electricity. So that's why efficiency is extremely important to us as well. When you put all the data centers together across the planet, you realize that it's a problem. Because when you look at the industrialized nations, if you put them all together, it would probably represent around the 5th largest consumer or producer of electricity, which is France, ironically. What's interesting about France is that it has 89% of its electricity generated by nuclear power. Okay, more than any other nation in that particular space. People always want to relate efficiency with greenness. Nuclear power is certainly the most green power. What's interesting also about France, since it just happens to be the country that fell there, they export 18% of their power. So the countries around them, they're not so keen on it necessarily because they build all those new plants at the border because it's easier to export the power. I thought that was an interesting thing. This is a breakdown of how the grid looks in the United States, or rather in North America. And what's interesting about this is that coal is at 39%. So when you plug that iPhone into the wall to charge it up, 39% of that power coming from the grid, because it's largely distributed, comes from coal energy. 30% from natural gas, 20% from nuclear power, then the others break down in little slivers. So it gives you an idea of where the juice is coming from that's helping you not only run your toaster, charge your iPhone, but run your IT as well. So what do we need to do? We need better, faster, more efficient components in the servers and in the data center itself. We'll talk about that. Let's harken back to the days of Intel's 486, right? Revolutionary new processor. It was fantastic because it had the math processor built into it. Many of us, recognize that as something that was awesome. And here's how we remembered it. Intel marketed it by its speed. They said, hey, you've got a 4633, you've got a cat's meow. I remember I had one, I thought, I'm awesome. And then Intel cleverly figured out, if we take the same chip, we overclock it to 66, like 67% of them still work great. So we stamped them all as DX266. That lets you overclock it to that higher speed. So now you got twice the performance for just a little bit more money. And then what they came out with the DX100, where they tripled the clock speed. So the same kind of thing applied. What's interesting, can anybody even tell me how fast their CPU is now? Probably not, because it has multiple dies. You're buying a Core 2 Duo, or you're buying an i5 or an i7. Marketing has totally changed, because what's important now? What's important is what's happening with the thermal envelope and what's happening with the power. So again, when that 46 came out, if you turned that PC on, you burned the same amount of power, whether it was idle, or whether it was running at 100% CPU utilization. It didn't matter. It chewed up the same amount of power. Here's what's happened in the last few years. What you'll see is that the operations, the number of transactions you can get, sorry that's kind of hard to read, are much higher on the new CPUs, but the thermal envelope, the power, is much lower. And what's interesting is it can have a rate that can be 2.5 times different from idle to full power. So we're getting smarter on how the CPUs can scale under workload. So here's Intel's latest roadmap. This is the Ivy Bridge. It's just come out. When they released it, 28 new processors were announced. And again, what's the most important thing? They're going to tell you how much cache they have. They're going to tell you how fast they run. But really what everybody covets now is this one right here, that thermal envelope, that thermal demand power. It tells you how much electricity it's going to take. It kind of governs how many you can put into a chassis. It governs which one you might choose for a laptop architecture, because the more power it takes, the shorter your battery lasts, things of that nature. And then the Intel Atom processor, what's nice about that? Very a decent chip speed, but very low power. So what's happening in the world of disk drives? This is the most amazing thing. How many of you have SSDs in your laptops? Right? Absolutely fantastic. We mandated we'd have SSDs in our laptops at work. Here's what we got. First benefit, I travel all the time, so once when I dropped mine at the airport, of course I gasped. Then I went, I'm okay, it's an SSD, it's not going to bounce the head. I turned it on, it didn't crack the screen, I'm working again. You do that with a regular hard drive, likely game over. So I got more robustness. More importantly, my battery lasts like 3 hours longer. That is incredible. So the SSD is about an order of magnitude lower in power. This little thing right here, I can put this up here to show you. That's the connector that connects power to the hard drive. From an engineering perspective, that was designed to be able to deliver 19 watts of energy to the drive. You take a 300 gig spinning disk. I had a conversation with a guy who had a cool title. He was a Seagate Fellow. I aspire to have the title of Fellow someday. But the Seagate Fellow, he said something interesting to me. He said, Jeff, he goes, in 2 years, we're going to no longer talk about spindles at all. It's the hard drive, the spinning mechanism. We're not going to talk about that at all because SSDs or flash drives, they're going to totally change the industry, and we don't have to worry about that RAID configuration anymore like we do today. So I'm going to prognosticate here a little bit and tell you that the 300 gig, 15,000 RPM drive, that's game over. That's the last one you're going to get of that architecture. Nobody wants to invest any more money to get anything better or faster because SSDs have hit that sweet spot finally where you can buy those and take, instead of 16 watts, an SSD chews about 1 watt. And if it's in stasis, that's to say it's idle, it chews about 1/10 of a watt. So an order of magnitude less than the 1 watt. And here's another remarkable thing about SSDs. The IOPS, the number of IOPS, the I/O per second that you can get from them, absolutely staggering. It's like talking to memory, so that's what's so nice about it. As long as we can keep the interface speed at a reasonable rate, we can get remarkable IOPS. We move the information faster to the CPU that are already running at multiple gigahertz to get the data in and out. Same thing's happening on the network side. I'm kind of old school when I say fiber, and you're with the cadre of folks that fit the old school moniker, they typically think of something that's orange, right? Fiber's orange. That's kind of changing today. It's changing to this color. It's called aqua. It's called aqua for a goofy reason. It's kind of a marketing thing. It's extruded. The silicate is actually extruded through heavy water. And as they extrude through that heavy water, something happens to it, and it eliminates any attenuation that it had in that 10 gig spectrum. That's the speed limit of your fiber in the data center. When it's on this multi-mode cable right here, 10 gig is the speed limit. Don't go faster than that, it's not rated for it. Here's what's interesting. There've already been 2 new standards ratified. We already have 10 gig, 40 gig's been ratified, and 100 gig's been ratified. So you go, well, Jeff, how do you get to 40 gig? Use this right here. You fire 4 transmits and 4 receives at the same time. Has to arrive at the other end within 79 nanoseconds because it's 10 gig, or 40 gig rather. You can't have a problem. How do you get 100 gig? You do 5 and 5, and then you use 2 of these at the same time. So there's where 100 gig is going to come from. IT infrastructure has to change. Guess where it's going to hit you? Right in the billfold. So get ready for that. But here's what's nice about it from an efficiency standpoint. You look at the old school servers, and this is what happens. You have, if you're running a virtualized environment, you'll have 2 network ports, gig ports for your VM network, 2 of them for your vMotion network, 2 of them for your vCenter console, 1 for backup, 2 fiber channel ports. Good Lord, that's a bird's nest. That's really what it looks like. When we moved to our cloud environment, we leveraged a converged network. And this is the back of the server. This is a UCS server. Look at that. That's beautiful. 4 power ports, 4 network ports. So in this particular configuration, this one can push 40 gig through a converged network. It does fiber channel over Ethernet. And everything's VLAN tagged inside there, very clean. It's a heck of a lot easier to configure 4 ports than it is this Go Rodeo here. Here's the front side of what that server looks like. Again, Virtualization is wonderful, a lot of savings there. We've had one particular customer, when they virtualized their environment, they were getting about 50 virtual machines per blade. We don't recommend that, but maybe there's an indication of how inefficient they were running their servers. But you think about that, this holds 8 blades, 50 servers per blade, remarkable savings in power. So if your SAN just isn't fast enough, you can move your SSD, put an Uber SSD in on the PCIe bus. And what's interesting is EMC just bought a company that does this. Fusion IO is out there. Wozniak, who was with Apple, he's involved in one. Remarkable processing, or excuse me, remarkable speed of IO, because it's all solid state drives on there. And it's tied into the PCIe bus, so remarkable throughput. This is something, if you have to have the I/O, this is the way to go. Next up is ReRAM. ReRAM is brand new. ReRAM is a type of RAM that has been patented by Panasonic, I believe. And here's what's cool about it. DRAM, which is what we have in the servers, dynamic RAM, is called dynamic RAM because every clock cycle, it wants a little bit more power to remember what it was doing. So if you're at 3.1 gigahertz, 3.1 billion times a second, you're sending it a little refresh of power to keep it whole. ReRAM says, I don't need the power. It's a little bit more complex gate to make, but listen, this is silicon, these folks will figure it out, and soon enough, I think we'll see ReRAM creeping into our servers. I took the liberty of translating the Mandarin Chinese, and pretty much it says your battery's going to last a lot longer, so it doesn't say that. But so here's another route you can go. Let's say that it's not storage or RAM that's your problem. Let's say, for example, it's actually compute, and you have a mathematical issue you're trying to solve, and you need lots and lots of compute capacity. NVIDIA first came out with a clever solution where they took their graphics processing units, GPUs, because they're fantastic, they're cheap, and easy to produce, and they were using them to offload the CPU and do the math on the GPUs. Well, Intel, not wanting to be outdone, did the same thing, and in this particular processor complex, the feed complex, you slide it into a PCIe slot, and you can have terahertz computing right in one box. Low power. I say low power, it has a fan. Why does it have a fan? Because it drinks a little bit of electricity and it has to get rid of the heat. So here's a real life example where somebody used low power in a pragmatic application. When Mozilla released Firefox 4.0, they did those millions of downloads all served from one server. It was called a C microserver, and it used these very tiny Atom processors, which are very low power from Intel. And they had, I believe, about an 80% savings per HTTP GET, which is what they do. They measure it on each GET, each request from the server. So remarkable efficiencies gained by using this. It was so good, I think it ticked off AMD. AMD bought the company. I don't think it has Intel chips anymore.